What we'll do now is, do you all have that entered? Yep. Compile to assembly. This time we're going to target JIB. So JIB is a proprietary processor. It's a little bit simpler machine code. x86 is kind of complicated. That's why we're using it. So copy this assembly code. It looks very much like x86. And once that's copied, head back over to your share folder, and you'll see jibc.exe. Open that up. And copy the code that you got from the OmniCalcs program into this leftmost window here. So what you're seeing right now, this is an assembler. This is taking our assembly code and assembling it into machine code right before our eyes. So it does it immediately. You can change registers and see how it changes the assembly or the machine code. Just make sure you change it back, otherwise it won't work. All right, does everyone have some machine code in front of you? Does it look like what you're seeing up top here? So what I did is I made it half screen. You'll see why in a bit. You might want to do that. To do that, you can just drag it to the left side here. So radix, we can set it to binary if you want to see the binary code. We'll leave it hexadecimal because that's a lot easier. We're going to go ahead and split by a byte. Byte, for those who don't know, is 8 bits. 8 bits in binary is 2 hexadecimal digits. And finally, we'll split by commands. So that just puts each command on a new line, makes it a lot easier to understand. So what we see here is 20 is our move, or sorry, is our jump. So we jump to 00002E, which is down here. That's a value, and that is our beginning. So we start by 10 is move, so we set SP to 500, DI to 100. So 500 is 1F4, 100 is 64, right? Because 60 is 6 times 16 is 96, plus 4 is 100, right? And then 44 is our XOR. So we have the first byte is our opcode, and then we have whatever registers we're working with, and a constant value, which is 32 bits, and that makes it 4 bytes, right? So in this case, we have varying length machine code. You don't have to understand the mapping directly, because that's why we have assembly, but just kind of understand that each line is one command. Is everyone at that point? Okay. Yeah, maybe do you mind helping Sarah? What we'll do now is, if you see on the slide, you might have to click this down arrow, this little emulate button with a green arrow, click that. And we'll put that on the other side of the screen. And then hit the load at the top of that emulate screen. And I'll make it a bit bigger, just so it fits. So does everyone see a big, ugly screen full of hexadecimal here? And you see the registers down the side here. So a couple things to note. We have our flags register, which is a special register. Remember how we had that comparison and then jump not equal? That's one of the bits in our flags register, and that is our ZF, stands for 0 flag. 0 is just another way of saying they're equal because the difference is 0. Computers normally use differences to calculate equality. The other thing you'll notice is the first value that's highlighted is this hexadecimal for 20 is jump, and then 04 just tells us what type of arguments it's taking, which in this case is a constant value, and that's the only one. So 0 because it's just one argument, and 4 because it's a constant value, and 2E. And take a look down here. We have our addresses right here. So 20 through 2F, and 2E is the second last one. And take a look at that. That's 10, 28, and then this constant value, 1F4, that's this first one here. So jump 2E tells it to jump to this value, right? And that value is the machine code of the first instruction we want to run. So we're going to go ahead and step. And step then sets it to that value. Notice that IP changes. IP is now pointing at that value. Actually, it's pointing at the next one. Right? And you can see up top here the disassembly. So this says move is our first opcode, SP is the register, and the value 500. So that sets our stack pointer to 500. That just tells the computer where in the memory we're going to put the stack, right? And now I'm going to go ahead and hit tick and then say 0.1 seconds. And this is going to go through. And each time it's running one machine or one assembly code in the machine code. It's incrementing IP each time, except for when it gets to that jump not equal, in which case it's going to jump up. Take a look at the registers as they're changing, right? CX is our counter. It's counting up by 1 each time. DX is our sum. It's counting up by n each time. Our DI is 64. That's 100. That's what it's going to end on. And what else is changing? IP is changing because we keep changing the instruction we're running. That making sense? Yeah, so IP is the instruction pointer. Yeah, it's supposed to be moving. It points to which memory address the instruction we're currently running is. So what you can do, hit tick again to stop it, and then just click start. That's going to run it, oops, not start, sorry, click run. That's going to run it really quickly and finish.
It loops until you get what? Like, is there...
Right, so it loops. If you look at the assembly code,
J and E loop, compare GX to 7 and then loop around until we had 7. There, is it going to be the same thing?
Kind of. So in this case, we're not comparing a register to a value, but CX to DI. DI is 100, and CX is counting up each time. Okay. So when CX equals 100, then it's going to stop. Yeah, so it's comparing to DI, which is 100.
Is it supposed to happen?
Yep. Yeah, so when you finish it, it's going to say exited with code 0. Code 0 means it ran properly, which is good. So exited with code 0, and you can take a look at our DX, 13BA. So that's 13BA, that's hexadecimal. Go ahead and try to calculate what decimal value 13BA is, and see what you come up with. So make sure if you're having a problem with it throwing an exception when you try to load, make sure that you're adding that @reg capital to the end in your OmniCalcs program. I'll show you what I'm talking about. Right? This part is very important. Anyone calculated what 13BA is in decimal? Sorry? Yeah, it's 50-50, right? Any surprises there? Right? So we just ran our machine code from our compiled assembly that calculated 50-50, which was the exact same as when we ran using our interpreted language. Anyone having trouble with this? Not getting 13BA? Okay, so for those of you who are done, which I think most of you are, crunching through 13BA, I'll just quickly go over how to actually do that. So we have our A, which is 10, right? Because A comes after 9 is 10, in the ones place. So that's okay. And then B is 11 in the 16s place. So times 16 plus 3 times 16 squared. So 16 squared, which is 256, plus 1, so 13BA, times 16 cubed. Right? That's our base 16 system. So we have our ones place through our 16 cubes place. We multiply those together, and we get 50-50. Okay, we ready to move on? This making sense to everyone? Right? So we've seen now, from the ground up, how we can do some fairly complex calculations using computers on CPUs, on processors, etc. Head back to the presentation. So the last thing we can talk about is peripherals. So we have our CPU that we looked at in depth. Peripherals are things that we actually use to interface with the computer. So for instance, how a mouse did work in very early versions of DOS is it would set 2 of the registers to its X and Y coordinates. A third one to certain bits stood for whether the left, right, or center button was pressed. And we could call a bit of hardware and software code that would look at the mouse, however it was plugged in, set those registers, and our program could use it. A keyboard worked similarly. We have a code for each key, like what we saw in that string for %D. When that was pressed, it set that into a register. And a screen just looks at a portion of the main memory. So we can set a bit of main memory, and that will change that color of that pixel on the screen. So it's a big array in the main memory that we render as a picture. The most important one that we'll get to a lot in the course is a bus. A bus is, in computing, something that can communicate two ways. So for a wire, remember how we had that 8-bit wire that carried the number 97? That only carried it one way. We could put 97 on one end, read it from the other. If we try to do the opposite, we're trying to write the same number to both ends, and it's not going to work. Because if we try to write both a 0 and a 1 at the same time, it's going to short circuit. A bus allows us to communicate in two different directions, and that's the basis of most of the network stuff we're going to be getting to in the next module. So there's our universal serial bus, for instance. So, speaking of, let's use those buses. So now we know how computers will actually compute. Now let's talk about how they talk. So we use a lot of different protocols for how they talk. We'll probably get about halfway through this before lunch. And we'll look at, from buses up, how you can connect to the internet and get Google and get it back to your computer. So let's take a look at what a bus actually is. In its simplest, it's nothing but a transistor. It says, I'm going to either connect you or disconnect you. If you're disconnected, then you can write, or then you can read, right? So we're going to connect one of these two. If it's connected, we write into it. If it's disconnected, we can read from it. And with just one connected, then we can send or receive information over this wire, right? Take a look at the back of your computers. Those Ethernet cables. Do you guys all know what an Ethernet cable is? So it's the internet cable. Usually they're blue. I think they might be white on here. They have 8 different prongs, and they give your computer internet. All they are is 8 of these. And that's how you can send and receive over the same cable. Let's look at what happens inside our Ethernet cable. This is a lot of different crap. Our actual data is here, and up here is what tells us where it's going, what it's coming from. So the first thing we send is a preamble. It's just 010100101. Actually, opposite around 10. What that does is allows the sending or the receiving computer to synchronize with the speed of the sending computer, right? We have a lot of different bits here, not just 8. So you have to send them sequentially, one, then the next, and the next. This alternation tells us what speed we're sending it at. Once it's figured it out, it gives us 11 at the end to say we're done the preamble. Now we're sending the destination media access control address. Anyone heard of a MAC address before? A couple people? So a MAC address is an individual address associated with every piece of hardware connected to a network. And it basically allows Ethernet to say, this packet's supposed to get here. If it's not there, something went wrong, don't worry about it. And the source MAC address. That source is where it came from, and that's so that we know when we receive a packet, where do we send it back? Yes, okay, your name, I should know this. Francois? Okay. It's like an IP address, but it's a level below that. So an IP address is an internet address that's global. A MAC address is for every piece of hardware. So it's 6 bytes instead of 4. So we see each byte is 2 hexadecimal digits, and we have 6 of them, right? So this is what a MAC address might look like. And it's different than an IP address. Yeah, so then we send the length of the message, and that length is in bytes, and the message itself, which is just data. And the last thing we send is a pad, or the second last thing is a pad. In case it's shorter than 64 bytes, we need to make it 64. The reason for that is, if it's shorter than 64 bytes, we might send it, and then we will finish sending before the next computer starts receiving. The problem with that is, the next computer might try to start sending something. And if we have it sending at the same time, we're going to be driving 2 different values on the same wire. It'll short circuit, bad stuff happens. So we want to make it a certain length minimum to make sure that doesn't happen. The last thing we do is a checksum. So what a checksum does is it adds up all the data in here, right? and it adds it up. If we add it up, it's going to give a very big number, so it throws away the last couple bytes. And it just takes 4 bytes from that sum. And those 4 bytes should be the sum of this. If it's not, so the receiving computer checks the sum, and if it's not, it says something went wrong. Sometimes it can use the checksum to fix data that it didn't get. Other times it can say this is too damaged, send it again. And that's the basics of how Ethernet cables work. So when you send some data, it adds this header, it adds that checksum and pad footer, and it'll send it along. Any questions? So Ethernet works well when computers are physically wired, but they are not. They can be wireless, and more importantly, they can be half a world apart from one another. How do we communicate half a world apart? We use what's called TCP and IP. They usually work so closely that they're combined, but they're actually different protocols. So we see a lot of P that stands for protocol. Protocol just means a set way of communicating data. And protocols literally make the web go around. So we've got a lot that we'll look at a bit later on in this module. And IP is the next one. So it's the next step from Ethernet, and it tells us how to connect beyond a single wired connection. So we can connect through routers and switches and other computers and all that. So IP, we now get into IP addresses. So that's what you were mentioning before. IP addresses, like Mac, are 6 bytes. IP addresses are 4 bytes, which is 32 bits. So here's an example, right? So 0 times, that's hexadecimal, and then we have 8 different digits, which is 4 sets of 2, which is 4 bytes. Is someone at the door? No. We don't normally write it like that, because that's kind of ugly. Humans don't read that very well. We normally, first we take it and split it into each 4 of the 4 bytes, and then we convert it to decimal. Right? And that high order byte, so high order is the first one, 54, we kind of split that up by area of the world. So we have North America takes this section here. It's kind of, we have 16 by 16 is 256 totals because we have 256 possibilities. We've got Europe and Russia right here, a bunch of other ones. And also in the early days of the web, they allowed companies to purchase IP blocks. So that's why we have companies like HP and AT&T up here, because they decided that they'd purchase it. It turned out to be a very wise investment. IPs are about, one sold for about $11.50 per IP, and that's 256 times 256 times 256 of them. So that's a couple million. More than a couple million, a couple billion. A couple $1 billion that purchase 30 years ago is now making these companies. The reason for that is, even though it's 256 times itself 4 times, we have so much on the internet, all of the IP addresses have actually run out as of 2011. That's why we're switching to a new system that uses 6 bytes, like the MAC addresses, but IPv4 is what we'll work with in this class. Yes? So initially they were bought by companies, and then it expanded beyond America. You can see most of these are American, and now they're handled by these regional internet registries. Pardon? Governments aren't allowed to buy them anymore. So what happens is their top level control is the regional registry. So say for North America, then North America says, okay, Canada can have this many, America can have this many, and then it's up to the Canadian and American registries to divvy it out within the country. Yes, Edwin. So the gray sections are multicast and future use. These are sort of like internal for more specialized uses. They're generally not for the World Wide Web, but they are needed for very large data centers that work inside each other. So what happens is you can use one of these within your own specialized data center, and then another data center down the road can use the same one. Since they don't connect to the internet with those addresses, they can both use the same one. Helps alleviate the problem of running out. Right, so we have these 256. What's of note to us is this one here. This was bought up by Merck & Co. They're a pharmaceutical company. Don't know why they need IPs. But what Amazon said to them a couple years ago was, can we have about 30% of your IPs? And they paid him a couple million for it, and they got it. Merck & Co. is 54, and so Amazon now uses 54-based IPs, and will be creating websites with 54-based IPs. So that comes from the fact that Merck & Co. originally purchased those, and they were willing to sell it to Amazon, about 30%. Very, very good purchase for Merck & Co. You'll also notice down here, these were the last blocks allocated. They're split up a lot more because that was when IPs were really running out and they had to split them up much more granularly. What time is it?